Welcome to a lesson on how to use a Caeser cipher with a shift to encrypt and decrypt a message. Both the substitution and transposition methods discussed so far are shared symmetric key methods, meaning that both sender and receiver would have to have agreed upon the same secret encryption key before any messages could be sent. All the methods so far have been susceptible to frequency analysis since each letter is always mapped to the same encrypted character. More detailed methods get around this weakness. For example, the Enigma machines used in World War II had wheels that rotated. Each wheel was a substitution cipher, but the rotation would cause the substitution used to shift after each character, and therefore reducing the risk of frequency analysis. For a simplified example, in the initial setup, the wheel might provide the mapping given here. Notice how we're mapping the entire alphabet as well as the numbers 0 through 9. Notice A maps to D, B maps to E, F maps to C, and so on. Since D is 3 positions to the right of A, notice how this would be a shift of 3. However, after the first character is encrypted, the wheel rotates, shifting the mapping one space, resulting in a new shifted mapping. So if the mapping shifts one more position, we can think of this red row as shifting 1 unit in this direction. If that happened, notice how now A would no longer map to D, A would map to E, B would map to F, and so on, which is shown in this mapping here. Using this approach, no letter gets encrypted as the same character over and over again. Let's take a look at an example. We want to encrypt the word court using an alphabetic Caesar shift cipher that starts with a shift of 2, mapping A to C, and shifts 1 additional space after each character is encrypted. Notice how this first mapping shows a shift of 2. A is mapped to C, B is mapped to D, C is mapped to E, and so on. So we'll use this mapping only for the first letter of C. So notice that C maps to E, so our first encrypted letter is E. Before we encrypt the next letter of O, we'll make a shift of 1 more position. So we can think of moving this row here 1 position to the left, which means now A would no longer map to C, A would map to D, B would map to E, C would map to F, and so on, which is already shown in the second mapping. So we'll use this mapping for the letter O. So O would map to R. Now it does get time consuming to make these new mappings every time, so let's make adjustments to this mapping for the last 3 letters. We would now shift this 1 position, and now we can encrypt the next letter of U. So before U mapped to X, but now with the extra shift, U would map to Y. So the next encrypted letter would be Y. We'd shift this 1 more position and then find the mapping for R, which means for R, we'll map this 2 more additional positions to the right, so R would map to W. And then for the final letter T, we would shift this 1 more position, and therefore using this mapping, T would actually map 3 more positions to the right, so T would actually map to Z. This would be the encryption for the word court. Now let's take a look at an example in the opposite direction. Let's decrypt this word. If it was encrypted using an alphabetic Caesar shift cipher that started with a shift of 14, mapping A to O, and then shifts 1 additional space after each character is encrypted. So this first mapping maps A to O as described. This would only be the mapping for the first letter, or Z. So to decrypt this, we would find the red Z, which is here, and therefore Z would decrypt to L. So the first letter would be L, and now this would have been shifted 1 position in this direction, and therefore L would no longer map to Z, L would now map to A, which we see here in this second mapping. So we'll use this mapping for the second letter T. So if the encrypted letter was T, Notice how the original letter would have been E. Instead of creating a new mapping each time, let's adjust this mapping to the next 3 letters. So before decrypting Q, we would shift this 1 position. Therefore, E would no longer map to T, E would map to U. So to decrypt Q, Q would actually decrypt to A. The next letter is J, so before decrypting J, we would shift this 1 more position. So here's J. Instead of decrypting to T, it would actually decrypt to S. Now we'd shift this 1 more position and decrypt L. And because we shifted the position once 3 times, L, this encrypted character here, would decrypt to 1, 2, 3 to T. So the original message was the word least. The actual Enigma machines used in World War II were more complex than our examples. Each wheel consisted of a complex substitution cipher, and multiple wheels were used in a chain. The specific wheels used, order of the wheels, and the starting positions of the wheels formed the encryption key. While captured Enigma devices provided the Allied forces details on the encryption method, the keys still had to be broken to decrypt messages. These code-breaking efforts led to the development of some of the first electronic computers by Alan Turing at Bletchley Park in the United Kingdom. This is generally considered the beginning of modern computing. In the 1970s, the US government had a competition and ultimately provided an algorithm deemed DES for Data Encryption Standard to be used for encrypting government data. It became the standard encryption algorithm used. This method used a combination of multiple substitution and transposition steps, along with other steps in which the encryption key is mixed with the message. This method uses an encryption key with length 56 bits, meaning there were 2 to the 56th power possible keys. This number of keys makes a brute force attack extremely difficult and costly, but not impossible. In 1998, a team was able to find the encryption key for a message in 2 days using about $250,000 worth of hardware. However, the price and time will go down as computer power increases. From 1997 to 2001, the government held another competition, ultimately adopting a new method deemed AES, which stands for Advanced Encryption Standard. This method uses encryption keys with 128, 192, or 256 bits, providing up to 2 to the power of 256 possible keys, making brute force attacks essentially impossible. I hope you found this lesson helpful.